Hi! Today I want to talk about something which is very close to my heart, namely gravitational waves. I'm a master's student in theoretical physics and I'm working on numerical relativity, i.e. gravitational wave theory. I'm planning on making a series out of this, explaining the physics behind my project and eventually lead up to what I'm actually researching myself. Today we are discussing gravitational waves. So let's start with the very basics. What are gravitational waves? Gravitational waves are a prediction of Einstein's theory of general relativity, and they are about as key to the theory as the expansion of the universe and black holes. So Einstein predicted that very massive and accelerating objects will distort space-time such that waves will form that will travel away from the source, just like a wave on a water surface would. And that is why you might have heard of gravitational waves being described as ripples of space-time, because that is exactly what they are. Perhaps you're even wondering why the detection of gravitational waves was such a big deal. Well, historically physicists have had to rely on electromagnetic radiation, such as X-rays and radio and microwaves, etc., etc. The detection of gravitational waves therefore opened up a whole new window into the universe, and things like colliding black holes, which don't emit electromagnetic radiation, are suddenly open to us. So I don't want to go too much into the mathematics here because I don't know who's watching, but I do want to tell you some things. So in general relativity, the geometry of space-time is contained in something called the metric tensor, denoted by g mu nu. The metric tensor defines notions such as distance, volume, curvature, and separation of future and past. Now, very far away from the massive objects that generates the gravitational waves, gravity is very weak, and that means that space is more or less flat. So in that case, you can think of the gravitational waves as being a perturbation of the flat space. This perturbation is denoted by h mu nu, and the equation of propagating gravitational waves outside of the source is given by the derivative of h mu nu, where the box is given by the second time derivative plus the second space derivative of the perturbation. And the 1 over c squared implies that the gravitational waves travel at the speed of light. In physics, this is known as the traceless transverse gauge. This particular choice is very convenient because what remains in the equation is just the physical information about the radiation. Another thing is that this choice also illustrates that gravitational waves only come in two polarizations, just like electromagnetic waves. The polarizations are denoted by H plus and Hx based on how they move when interacting with particles. And any gravitational wave can be described as a linear combination of these two polarizations. You've most likely heard of the first detection of gravitational waves being done by LIGO in 2015. LIGO stands for Laser Interferometer Gravitational Wave Observatory, and it is built in an L shape with two equally long 4-kilometer arcs with mirrors at each end. Light is bouncing from each arm to the mirror and then back again to the corner station where an interference pattern can be observed. The gravitational wave will stretch space in one direction, squeeze it in the other, and then reverse the distortion. When a gravitational wave passes through LIGO, one leg will be lengthened and the other will be shortened. That means that the light from one leg will arrive at the corner station later than the other. Remember that these gravitational waves come from merging black holes many light years away from us, so needless to say this effect is incredibly small. Actually, it's 10,000 times smaller than the size of a proton. This is why the arms of the detector needs to be so long, and in fact they should actually be longer. But remember the mirrors at each end. They are built in such a way that the laser beam actually bounces 300 times before merging at the corner station. This increases the distance each laser beam travels to 1200 kilometers. And increases the sensitivity of LIGO even more. This development and many others is what made LIGO sensitive enough to make the very first detection of gravitational waves in 2015, 100 years after Einstein had first theorized them. So important that absolutely no one was surprised when the discovery received the Nobel Prize in Physics 2017. And now when we have gravitational waves, the question remains, what can we do with them and what do we still have left to discover? Well, one thing to remember is that the only detections of gravitational waves so far have been from single catastrophic events like colliding black holes. One thing that we have yet to observe are continuous gravitational waves. These are thought to be emitted by rotating neutron stars, for example. And we have simulations of what such a signal would look like in LIGO, but we have yet to detect it. And the thing that I'm mainly focusing on is dark matter detection. So the particles that I'm studying will actually emit gravitational waves either by annihilating with themselves or by influencing the massive objects that they are surrounding. And this and many other things is what I will discuss in my next video on this topic. See you then. Bye!